Hey guys, this is Darshan Lokhande. I am a pre-final year BTech CSE student at IIIT Pune. Welcome to our channel Learn Competitive Programming with CodeChef. If you are interested in competitive programming and want to learn data structures and algorithms, this is the one-stop destination for you. We post weekly problem explanations and concept videos. So don't forget to subscribe to our channel by hitting that subscribe button and also the bell icon. The problem that we are going to discuss today is Scalar Product Tree. The problem appeared in November Long Challenge and has a difficulty level of medium hard. The prerequisites for this problem are trees, square root decomposition, and pre-computation. Our agenda for today's video is going to be as follows. First, we will walk through the problem statement and try to understand what the problem is trying to say. Then, we will see the detailed solution approach to the problem, followed by which we will be seeing the time complexity analysis for our implementation. Then, we'll see the pseudo code and then have a quick go through of the C++ code. The problem statement goes as follows. We are given a tree with n nodes where n vertices are numbered from 1 to n. Also, the tree is rooted at node number 1. So let's say, for example, we have a tree with us, then the node number 1 is going to be our root. Also, it is given that the ith vertex has some weight associated with it. So over here in our example, we have the weights as 3, 6, 4, 2 and so on for each node. Okay, so let's say that we choose a particular node. At this point of time, I would like to mention that if you haven't yet tried the question, give it a try and then come back to the video and continue with the editorial. To start off with our solution, a naive approach to the problem can be that we can apply a DFS on the given tree from the root so that we keep a track of parent node of each node. That is, if we have a node, we know who its parent is, right? So once we have applied this DFS, what we can do is that for each query, that is U and V, we can start with the given nodes and then at each step we can go to its parent node. Okay, so we can go to its parent node and we just keep doing this until and unless we have reached the root. So what will happen is that iteratively at each step we will be going up by one level, and while doing so we can always keep a track of the dot product. Okay, so we can keep the track of dot product by multiplying these weights. Okay, so let's say this is Wi and this is Wj. So Wi into Wj. We just keep adding this in our dot product for each of the current node that we are at, and at the end we will be having our dot product. So this naive approach can definitely give us a solution, but at what cost? Because as you can see that for each query we have to travel all the way from the given node to the root, right? So that is order of n complexity per query. So it will definitely not work for 100 points because the constraints are n and q can be up to 3 into 10 to the power 5. So it can definitely not work. But you can always get subtask 1 right because there the constraints are pretty small. So although this approach is correct, but it will not work for higher constraints. So let's see how to optimize this approach to fit for the given problem. So for the original constraints, we have to optimize our method by doing some kind of pre-computation. So let's say that for a particular level, that is, let's say level X, we are pre-computing the answers for all pairs of nodes. That is, if any pair is given from this depth, we can directly give its answer. So what will happen now? So let's say for a particular level Y, we are given the query, that is two nodes u and v. Then what we can do is that we can naively keep moving up one step at each time to its parent until and unless we reach this level x. So same for the node v as well. So what we will do is that As soon as we get the query, we keep moving up one level at a time until and unless we reach the level X. So because we know the answer for level X for any pair of nodes, so from there we can directly take the answer. We don't need to iterate from that level to root, right? So pre-computation helps a lot. But the question again now is that for which levels to do this pre-computation for? Because this was just one level, right? That is level X. So there are many such levels present in our tree. So we cannot do the pre-computation for all levels, right? So we have to choose some specific levels. So here comes the concept of square root decomposition. So let's see that how square root decomposition will help us achieve our goal. So we start off by dividing our tree into blocks of layers. So let's say that this is one block, this is another block, and so on up to the leaf nodes. So each block has same size, that is same number of levels. So let's say that the block size is small b. So for square root decomposition, small b is said to be root n, where n is the number of nodes in the tree. Okay, so we are going to divide our tree into some number of blocks where each block is of the size root n, that is it contains root n many levels. So what do we do after that? For each of these block, we will choose one level from each block and pre-compute the answer for that particular level. So which level to choose is the question. So for each block, let's say there are some number of levels available in that block. To take an example, let's say B is equals to 5 and the 5 levels are 6, 15, 5, 8 and 10. That is, the first level in the block contains 6 nodes. The second level contains 15 nodes and so on. So what we do is that we find the level in the block which contains the least number of nodes, and for that level we pre-compute our answer. What do we mean by pre-computation? So for all possible pairs of these 5 nodes, so let's say if there are 5 nodes, then for all possible pairs we calculate the answers and store them, okay, so that we can use them later. So we do this step for all the blocks, that is, for each block we find that how many nodes are present in each level, and whichever level contains the minimum number of nodes in that particular block, we pre-compute the answer for that level. So once we are done with the pre-computing part, for any query u comma v, what we do is that naively keep iterating upwards until and unless we have found a pre-computed layer. So now the point to observe is that at max we have to do only 2 into b steps. That is, in 2b steps we will definitely reach a pre-computed level. Why? Because the block size is b, right? So definitely if we are doing 2b steps, we will come across a level which has all the answers pre-computed. So for each query, we just have to iterate maximum 2b levels up to find a pre-computed level. So to understand that why square root decomposition works on this problem, let's try and understand the time complexity analysis of the problem. So we know that the block size small b is set to root n in square root decomposition. And let's say that the number of nodes in one block is capital K. So what is the minimum number of nodes in a layer in the block? So it cannot exceed K by root n. That is, small m, which is the minimum number of nodes in a layer in the particular block, cannot exceed k by root n. Why? Because if it exceeds k by root n, then the number of nodes in one block would be more than k, which is not possible, right? So the minimum number of nodes in a layer m is less than or equals to k by root n. After that, we can also say that the total number of pairs would be k by under root n whole square. The total number of pairs would be k square by n. So now we can also say that k square divided by n is actually less than or equals to k. Why? See it in this way. You can write it as k into k by n less than equals to k, and now we know that k is definitely small than n, so this thing is actually less than 1, right? So the left hand side would be less than or equals to k. So we can infer from the following analysis that the total number of pairs, that is k square by n, is less than or equals to k, and this thing is valid for a single block. Okay, so therefore we can say that for each block the total number of pre-computed pairs is actually less than or equal to number of nodes in present in that block. So if we sum over the pre-computed pairs for all the blocks, we can say that they will be less than or equals to n, the total number of pre-computed pairs. Why? Because for each block the upper bound was k, and if we sum up for all the blocks, the total number of nodes in all blocks is nothing but n, and the total number of pre-computed pairs for all blocks is nothing but what is present on the left hand side. So the total number of pre-computed pairs will be at max n, right? So from this we can now conclude to the time complexity. So because each pair takes order of B time for pre-computing, so we can say that because there are maximum n pairs, so the time required for pre-computation is actually O of n into root n. Why? Because n is the number of pairs and root n is our B, that is block size. So this is the pre-computation time. And also similarly for each query we would require order of B time for calculating its answer. So again, order of Q into root n, right? So this is for the queries. So overall, we can say that the total time complexity of the problem is order of Q plus n into root n. Why? Because n root n is for pre-computation and q root n is for the queries. So this is the total time complexity, and you can easily see that for the given constraints, that is n comma q less than or equals to 3 into 10 to the power 5, this can easily fit in the time limit. Also, did you know that CodeChef also conducts free live classes on Unacademy where we teach every possible topic on competitive programming? We have beginner level courses like Introduction to Programming in C++ or Java, basic data structures, recursion, as well as advanced courses like dynamic programming, graph theory, and segmentaries. These courses are conducted by top coding experts who have been ICPC World Finalists, IOI medalists, or have worked in top product companies like Facebook, Google, Amazon, LinkedIn. All you need to do is download the Unacademy app or register yourself at unacademy.com and select your goal as competitive programming. You can also take the paid plus subscription to get additional features and individual level support. In plus subscription, we have a large set of problems associated with each topic covered. Not only that, we also have 6-star and 7-star rated teaching assistants to clear all your doubts during and after the live sessions. Also, don't forget to use my referral code DarshanCool25 while subscribing to get an instant 10% discount. Now that we have seen the solution, let's get to the pseudocode. So the pseudocode starts with two functions, that is DFS and query. So the DFS function is used to calculate the parent of each node in the tree and also the dot product for queries of the type u, that is same node, same node, right? So, and also the query function takes two parameters u and v and returns the answer for the query. That is, for two nodes u and v at the same depth, it takes the input and finds the answer and returns it. So what happens in the query function is that we start with the nodes u and v, and until and unless they are not equal or we have reached a level for which the answer is pre-computed, we increment our total variable by multiplying the weights of the uth and the vth node. And also we change u to parent of u and also v to parent of v. That is, we move one step higher. Okay, and once this while loop is breaked, either of these two conditions will be true. Either u is equals to v. In that case, we have already computed the answers of the type u comma u. So if u is equals to v, then we directly increment our answer by dot product of u comma u, or else we have reached a level where the answer is pre-computed. So we increment our total variable by the pre-computed answer of the pair u comma v, and finally we return our total variable. So these two functions are going to help us in our main function. So in the main function, we start by taking the input, that is the number of nodes and the edges. After that, we create the tree and run a DFS to calculate these parents and dot products. And after that, we set our block size to be square root of n and then pre-compute the answer for each block by choosing the minimum level that contains the minimum number of nodes. And after the pre-computation is done, we take the input for q queries. And for each query, we just have to call the function query u comma v so that it returns the answer and we print it. Now let's see the implementation of the code in C++. So we start off by taking the input for the number of nodes and the number of queries and the edges in the tree, and then create the tree itself. Okay, so after creating the tree, our first task is to apply DFS on the tree so that we compute some necessary information. So we call DFS with the root. Okay, so once the DFS is called, what the DFS does is calculates the parent node for each node and also the depth of current node. Okay, and at the same time we are also updating the max depth because we are going to need it afterwards. So after these three things are done, note that we are also calculating the dot product for the current node. So this is for the type of queries such that query u comma u, that is, if the both the nodes are same, then the answer is nothing but the sum of multiplication of weights with itself. That is, if the weights occurring in the path from the current node to the root are, let's say, 2, 3 and 4, then the answer will be nothing but 2 into 2 plus 3 into 3 plus 4 into 4. So to avoid these kinds of queries later on, we are already pre-computing them for all the nodes. Okay, so that part is handled over here. And that's it. That completes our DFS. So going forward, we then store the nodes level wise, because in the DFS we now know the level of each node. So we are storing the or sorting the nodes according to their different levels. So let's say that if node number 1, 3 and 5 belong to level 3, then they will be pushed back into level of 3 and so on for all the nodes. Okay, so once we have stored the nodes level wise, we then move forward to the most important part, that is pre-computing the answer. So we set our block size first to be square root of n, and then in each block we first calculate the level which contains the minimum number of nodes. Okay, so we already know that each level contains how many nodes, so we just have to iterate over the all the levels present in that block and see which level contains the minimum number of nodes. Once we have that level, which is denoted over here by LV, for that particular level, we are numbering the nodes in that level for ease of calculating the answers for each pair. And once we have done that, we call the query function for all possible pairs in that level and store the answers in a vector known as memo. And once this task is done for all possible pairs, and we also mark the nodes in that level as true, so that it when the actual queries are given to us, we know that which of the nodes are actually the pre-computed ones. Okay, so we are marking these nodes as pre-computed. Then the last task is to answer the queries. So we take the input u and v and simply call the function query with the same parameters u and v. So what the function query does is it initializes a variable tot, that is total, as 0. Note that the variable is of the type uint, that is unsigned integer, because we have to report the answer modulo 2 to the power 32. So the unsigned integer part handles it. Okay. So as discussed in the pseudocode, we start with the while loop, where until and unless the two nodes are not equal or we have reached a pre-computed level, we keep incrementing our total by the product of the weights and go one step higher by changing u to its parent node and v to its parent node. So once we exit this while loop, either of the two conditions will be true. Either u will be equal to v or we have reached a pre-computed level. So if u is equals to v, then we have already computed the dot product in the DFS, right? For the queries of the type u comma u. So we increment our total and return it, or else we increment our total by the pre-computed value in our memo vector and then return our total variable. So in this way, we are solving the problem in an optimized manner. So without wasting any time, let's submit this code on CodeChef ID and let's hope for a quick AC. Great, so our solution works.